Yes, good evening. As per the time I'm making this presentation, welcome to this YouTube video presentation about computer vision, where we are bringing in different tools to develop a garden monitoring tool. So here we're looking at deep learning at a naive base to actually come up with a garden monitoring tool. SOLIMO RAJAB, registration number 2022HD051486U, with my student number stated there, and this is my computer vision presentation. So looking at what is going to be envisaged in the content, there is introduction, some of the works that have been reviewed as part of what is in the report, the methodology, the experimental setups that could have happened or that happened within the project, the results and analysis, come up with some conclusions, and we can look at some of the references to this. So, looking at the basis of this project, you see that computer vision combined with deep learning algorithm is a promising technology in the agronomic sector for the difficult challenge of automating the plant identification based on whatever characteristics, maybe the leaves and so forth. So precise crop type cultivation information is crucial for the sustainability of agricultural strategies and meeting the demands of foods in this changing environment. The agricultural sector is embracing a lot of the digital transformation and leveraging these technologies to enhance the food production and overcome the challenges that are being faced. And here we look at the machine learning techniques that have come into play to actually model the complex agricultural relationships and make predictions using that data that is captured from the agri sector. Computer vision technology in agriculture, now aided by the image sensors and algorithms, is crucial for accuracy of agriculture, and we can call it the smart agriculture development. In this project, we now say image-based methods for quick and precise crop identification based on the visual characteristics of the plant or the crop, while leveraging deep learning-based computer vision for automated garden monitoring is an urgent need in the agriculture sector today, where this project is basis that we need something that can actually give us a quick and precise identification of where this type of crop can fall in. Some of the related works that actually have come up with, people have come up with, those scholars have come up with. We have one study by Murawat with its partners in 2018, which used the blob analysis and SVM to develop an efficient wheat classification solution. This one achieved 50%, accuracy ranging from 50% to 95%, which was a bit fairer. Now, Kamaz, Balachandra, and Prabhu 2020 employed SVM and random forest to classify the wheats with random forest performing better with 86% and 73% of accuracy for SVM. Those are the local machine learning algorithm. One of it has been also employed here. That's the naive base. CASMI 2014 used the SIP futures to detect thresholds and sugar beets with 99% accuracy. See how things are playing. Now, deep learning approaches also have been utilized widely for plant identification, with the CNNs outperforming the traditional machine learning algorithm. That is one study by Hassan and a group in 2021. Transfer learning has also come into play, where this project is now coming in to adopt pre-trained convolutional layers to new data sets, significantly improving classification accuracy. That is one study by SAR in 2018 with a group. Olsen in 2019 fine-tuned the pre-trained ResNet 50 and Inception V3 models in their work to classify 9 species, and they achieved an accuracy of 95.7% and 95.1% respectively. Third, in 2018, compared back propaganda neural network and SVM models for weed detection in soybean plantation in Brazil. We find that the CNN performed better with 96.6%, while the local SVM machine learning model achieved 95.1%. In 2017, Ferreira compared the CNN's performance to the other post-random forest and SVM models. The CNN model performed better with 99% accuracy across all the photos of the crops that they were investigating. So, what is the methodology that has been applied in this study? Here we have employed two approaches. One is the naive Bayes, and then the deep neural network. So, with the naive Bayes here, you find that this classifier uses the Bayes theorem to estimate the probabilities of membership for each class, which means it uses that to determine the likelihood of whatever data which is given to it. This naive Bayes, in brief, we can say that the class with the highest probability is identified as the most probable class for this case. Now, looking at the deep neural network here, the deep neural network employs uses what we call the layers. These layers actually are the ones that convolute within the network until it finds whatever it needs, whatever features that it needs. So this model here is a model which is employed for the deep learning neural network, where there is, in the first point here, there is the data set which is acquired, which was acquired for this project, acquired locally. Then the pre-processing, where we actually come up with some preparation of the images, data augmentation, and so forth. We divide this data set into 80% for training and testing 20%. We build the model, we train this model, and then we actually evaluate this model using the accuracy, the precision, and recall, or the F1 metrics. The experimental setup in this project here, we find that yes, there was image acquisition, where the images which were used here were captured from a video which was recorded using what? A phone camera in a mixed crop garden. These images were actually snipped just using a local tool in a computer, and there were three classes of images or crops, where we had the maize, the cassava, and bananas, mainly for this study. Now, a total of 74 images were captured in this case. Cassava took 27, banana 16, and maize 31 images. During the preparation of the images, there was cropping, auto cropping of the images to a resolution of 224 by 224 pixels before we could fit this into the model. We also resize this to reduce the computational requirements, normalize the images for faster learning of the model. This is basically for the deep neural network model which was selected, or the deep learning model. This data set was split into 80% and 20% for testing purposes. So looking at here, these are the three classes of the crops, where we have maize in the train set having the highest number of images, cassava having second highest, and banana having the lowest count of images. Also, when it comes to the testing part of the classes, maize still had the highest, cassava had the second highest, and banana having the lowest. Right now, data augmentation this is basically to help us generate more images within the data set, so that maybe we can overcome the problem of overfitting. The data augmentation for this case increased our images from 60% to 68% for the training images, and then 14 to 24 images for the purpose of the training, and we achieved the 92 count of images from 74, which was initially acquired during the first stage of image acquisition. Feature extraction. Looking at the feature extraction here, we find that the deep learning has many layers or multiple layers that include the convolutions. We call them the convolutions, the pooling layers, and fully connected layers. These layers have a lot of capabilities that have been trained, so that yes, they can be used for learning and also extracting the features from whatever images that have inputted. So feature extraction in deep learning basically happens automatically within the neural network of the architecture or the model. As for the naive Bayes algorithm, I employed two local feature descriptors, that is the SIFT and the ORB, for extraction of features within the images. And looking at the first image here, this is an image of banana or matoke, where the sieve has been applied to extract the features for what? For learning and prediction. The second image here is the ORB feature extractor, also applied onto the banana to extract the features for the learning purposes. Looking at the metrics that are employed for this study, there are 4 metrics: the accuracy, the precision, the recall, and the F1 score. The F1 actually, this is the harmonic mean of precision and recall, whereas the accuracy here is we get it by taking the percentage of images whose classes are accurately predicted among those ones who are from the test images, and actually have indicated that their outcome is much better. So those are the 4 metrics employed for this project case. These images are images from the train model of the deep learning model, or the DNN model that is being used. So here it visualizes the banana or the matoke images. But when it comes to the testing or the validation, we see that yes, these images have also been classified slightly in an incorrect way, or we can say yes, because you see that the cassava images have been labeled as banana, and yet these are supposed to be different. So this one can give us the wrong these are the false truths in the confusion matrix or in the training of the model. Results and analysis. We find that with the deep neural network, which employed the ResNet 50 convolutional neural network, performed better with the 10 epochs that were actually we used for the model, giving us a train accuracy of 99% and the test accuracy or validation accuracy of 100%. So the model performed so well in this case. Whereas for the naive Bayes, through the 2 feature extractors took actually employed about 5 thresholds, where there was the first threshold which took 5, giving us for SIF 20% and 33 for the ORB. But overall, you see that for the naive, for the 25th threshold, the SIF performed better in accuracy, or yes, in feature detection, and ORB also performed a little fairly. So overall, you will see that the DNN model performed better than the naive Bayes, because the naive Bayes here gave us the 52% overall with the sieve with the sieve feature extractor and 40% for the ORB. So we see that for this overall percentage, we actually got it by actually summing up the percentages from the thresholds and then dividing by actually getting the average of whatever was gotten from. Now, the graphs here shows us how the loss and accuracy graphs for the DNN model actually move. So we see that for the train, it moves stiff, coming downwards from actually drop, and then for the train accuracy, there was also subsequent growth of the model. Here also the same visualization, but giving us the epoch, which best epoch did the model actually find it is best loss, and then the best what, the best validation or the best training. So all of them achieved at the 10. So in the conclusion here, we find that the study focused on focused on computer vision and deep learning for for crop identification. The dataset contained 3 classes of crops: maize, banana, and then the cassava. The deep learning performed better with 99% of train accuracy and 100% validation accuracy. The naive Bayes overall 52% and 40% based on the future descriptors, which is the sieve and the ORB. So here we find that the deep learning model performed or outperformed the naive Bayes in identifying the crops. So the deep learning's ability to learn features provided better image representation compared to the other model. So the limitations of the image acquisition method might have hindered the naive Bayes in its performance, and we can see that the computer vision and deep learning show promise for automating a variety of the mixture control. Suggested exploring methods for capturing high quality images so that maybe the models can learn much better in future. The last slide here gives us the links to the project code. So this is the link to the GitHub project. I thank you for